I'm Scott Walkinshaw. I work at Shopify here in Toronto, and I work on our API patterns team. And we've been responsible the past couple of years of launching a couple of public GraphQL APIs. We also have many internal ones, but we're going to be focusing on one of our public ones. And I'm going to be talking about GraphQL caching. And we're going to be using one of our APIs as an example of how to cache a GraphQL API. First, let's start with a really loaded question. Is caching in GraphQL harder? And I'm going to need your help. Who's read or heard that caching GraphQL is much harder or impossible or anything like that? All right, I'm raising my hand too because I've read this many times. In fact, I even know this from experience. So I hope you weren't expecting me to tell you that it was easy, because it's not. And it is hard. But I think pretty much all caching is hard, so this shouldn't be too surprising. And I'm giving a talk on caching, so I couldn't pass up a chance to use this pretty famous quote. There are only two hard problems in computer science: cache invalidation and naming things. And of course, I'm going to be talking about cache invalidation. And if you want an example of how hard naming thing is, well, I just kind of gave up and named my talk GraphQL caching instead of trying to come up with something a little more creative. And also, this is one of my favorite follow-up versions of that quote. Wait for the laughs to kick in. It's pretty funny. Also, I went through this, I wrote all these slides, and I realized that I use the term caching, I don't know, maybe 1,000 times in this talk, and maybe people aren't too familiar with it. So here was pretty much the most shortest definition I could find of caching. So just a general software component that stores data so that future requests for that data can be served faster. So usually we're concerned about performance here. We want things to happen faster. And let's go back to this. And so yes, it's hard, but I'm going to correct this a little bit. I think more importantly is that it's different. We can't just use the solutions that we're used to. We got to come up with some new ones, and they got to be more GraphQL specific. So the rules that we're normally used to for RESTful APIs may not apply here. I also use this term REST as kind of a catch-all. I think Marc-Andre actually had a much better term that I could have used here, just endpoint-based APIs. So not strictly REST, but anything that's basically an endpoint-based API. So as mentioned, we can't just carry over these solutions that we may have known for years. And so whenever I read anything or hear about GraphQL caching being harder, it's usually about HTTP caching. This is what a probably typical GraphQL request looks like. And most GraphQL APIs use the post method. So they post this JSON encoded body. That's true of Shopify's APIs as well. And it's also true that usually with post, we can't use normal HTTP caching solutions. Of course, we can use get methods. There's nothing in the GraphQL spec that tells us we need to use posts. In fact, they don't even say you need to use HTTP. But this is from the official GraphQL.org site, and it says, it should handle get and post requests. And of course, the get requests, we're just sticking the query string in a query parameter just like this. So we could use the get method and go back to HTTP caching methods. But I think that kind of leads to a bigger question, and that is, how useful is HTTP caching? And for us, more specifically, it's how useful is it for APIs? So this is my opinion, but what I think HTTP caching is great for is a couple of these situations. The first one, immutable resources with a very long max age. This one's easier to think about. You can probably think of, say, JavaScript or CSS assets, with a version or a hash in the file name. You set the max age to a year in the future, and instead of trying to bust that cache, you just deploy a new version. The next one is also mutable resources with a max age. So if you know when it's going to expire, or it's a time-based expiry, then that's also great. This means that the requests don't even have to go to the server, and that's the ultimate caching solution, is when we can avoid requests hitting the server at all. I think it's a bit less useful in all these other situations, which is a mutable resource where the server always needs to revalidate it. And for HTTP caching specifically, this means e-tags, or last modified timestamps. And by definition, this means the request has to reach the server, and the server has to set these headers of the e-tag or the last modified timestamp. This kind of leads to my first generalization of APIs. And most APIs deal with mutable resources without a max age. To use Shopify as an example, we have, say, a product resource, and that doesn't have a useful expiry. It can be mutated or changed at any point by a client or user, say in our admin or via an API client, and that should invalidate the cache. And I think that HTTP caching is really amazing when used by a web browser. So browsers have built-in caching capabilities, which you get for free. All you need to do is set the proper headers on your servers, like etags or max age, and the browser takes care of reading and writing the cache and invalidation, and you never have to worry about this. Unfortunately, it's a little less useful when used by pretty much any other client. Things like curl, or languages built-in HTTP clients like Ruby's NetHTTP or Node's Fetch, or your fridge. The great thing about coming after a speaker is you can steal their jokes. So at least I don't think fridges have HTTP caching built in, but I don't know. And this kind of leads to my second generalization, is most APIs are consumed by a wide variety of clients that we don't control. And so ideally, any client can benefit from caching without having to do anything. So I want to be very clear that HTTP caching is very useful in some situations, just a little less so for APIs. And I hope that I've shown that it's not the end of the world, that we can't use it with GraphQL. I mean, you could, but it's not the best fit. So where does this leave us? It kind of leaves us where a lot of people start by default anyway, and that's with application caching. Since the request is probably going to the server anyway, we can't avoid that. We want we want the caching to be transparent and available to all of our clients, no matter what they are. We may as well handle the caching ourselves at the application level. And there's many ways of doing application caching with GraphQL. I'm going to focus on one method that we use, but I don't really highlight these in slides, but just to give a couple other ways. Once the request is on the server, you could implement caching in a single resolver, for example. If you know one resolver is slow, maybe it hits an external API, you could always cache that. At Shopify, we have an open source solution called Identity Cache. This takes your Rails models and basically stores them in memcache. So we already leverage that in our resolvers. So you're free to take advantage of kind of any combination of, say, lower level or like single use case application caching techniques. But for this one, we're going to be talking about a full query cache. And here's kind of a flow chart of what this looks like. I'm going to break it down in code after, but kind of start from the top. Query comes in. First, we have a flag that's basically is cache enabled or not. So the easy path is no, the cache is not enabled. We execute the query as usual, return the result. If it is, cache is enabled, then we try to determine is the query document cacheable. No, again, execute the query, return the response. In the yes case, it gets a little more complicated. We generate a cache key, and we check if it's in the cache. If it's already cached, we fetch it, and then we return the result. So that's the kind of optimized cache hit path, which should be way faster. If it's not cached, again, we execute the query, and this time we also store it in the cache, and then we return the result. A lot of this is fairly standard caching solutions, but we'll get to some more kind of GraphQL specifics. Don't worry if you can't see all this code. This is kind of like a slightly edited version. We have a query class that is responsible for actually executing our queries and doing the caching. We're going to focus in on each part as we go through it. So first, we have a result method. And this is what actually executes the GraphQL query and just returns the result as a hash, and then that gets serialized as JSON out to the client. And you can see it's been wrapped in this kind of fancy with caching block. And here is the with caching method. So these are the first kind of two steps I talked about in that flowchart. Is first we just see if the cache is enabled or not. That one's fairly simple. It's just a flag. So this kind of says if caching is enabled and the query is cacheable, then try and fetch it from the cache. If the cache is found, we fetch it and just return the value. And that value is the entire response. We're using memcache here if you're curious, but any kind of caching or key value store or database will work. If the cache is not found, we execute this block and store it in the cache. And if you're not too familiar with Ruby, we're just yielding this block here, which ends up just executing the request as usual. So again, if it's a cache miss, we execute it, store the result in the cache. And this has all been fairly standard caching functionality so far. It's just the cache hit or miss and storing it. So now let's get into some of the more interesting bits. And that's this cacheable method. So this method looks pretty simple at the surface, but there's 3 important checks being made here. The first one is we just want to find out if the query or the document is even valid or not. If someone gives us a document that was just invalid syntax, we obviously don't want to cache it. It's going to return quickly anyway because it's just a static validation error, but we don't want to cache it, so we'll skip it. The next one, we check if the operation is a mutation or not. Mutations are write operations, so we don't want to cache those. And I mean, this is just the same logic that applies to not caching posts or puts in RESTful APIs. By the way, any kind of GraphQL server implementation you're using should probably give you a way of checking what operation the document is. And those first 2 checks would probably be standard across any GraphQL caching solution if you, say, implemented the same one. This one is a little more specific to our use case, and it's where it gets a little more complex. But before I jump into this method, I'm going to take a step back, and for every GraphQL request we receive, we analyze the document and collect all the types referenced. So here's an example query. You can see we're asking for the name of the shop. We have a connection of products, a couple fields, ID description, and some price range. And so this is the input that we want. And here's our output. We've collected an array of type names. These are all the types referenced in this query, minus scalar types. So you can see like amount, for example, is a scalar. So that field's type doesn't appear in the types used. Same with even description HTML, that's a custom scalar we have. It's like an HTML scalar, so that doesn't show up. So we have a types used class. It's actually fairly simple. It traverses the document and creates a set of all types used. I'm not going to explain this too much in depth. Again, any GraphQL server implementation you use should give you a way to kind of analyze the document. So this is the GraphQL Ruby gem. But briefly, we create an empty set of types used. We add the type as we go through. And then finally, we just recurse over the children, and we repeat this process all the way to the end of the tree, skipping the scalars. So now we can get back to the actual body, the types cacheable method. And this is where we collect the types using that class I just showed. So we'll have a set, I guess, or an array of all the types names used. Next, for all types to be cacheable, a few key things need to be true. First, it's not an introspection type. And second, any non-object type is cacheable, such as scalars. And finally, we check if we have set the type to be cacheable or not. I'll talk more about this, but this is a custom property that we've defined on our object type. So we made the concept of caching opt-in. We default to everything being not cacheable. So only if we're sure if a type is cacheable do we set it to true. So here's an example of a product type in our schema or in our code base. And you can see that we have opted into caching. We set cacheable true. If a lot of people here are familiar with JavaScript and defining your schemas, say like IDL first, I was glad in Erica's talk she gave an example of like defining your schema in JavaScript. So in Ruby, we often define the schema in code. So this is an example of the product type. And there's one more important detail that I've skipped in all this caching part, and that is the cache key. The cache key is kind of part of our invalidation strategy. So let's take a look at how we build our cache key and what makes it up. So here's what our cache key looks like. Slightly edited, but mostly true. First, we have kind of these, we segment it by shop and app. This is true of Shopify's domain. We deal with kind of shops, but say you were GitHub, you might segment this by organization or user, for example, and say your app or the API client that's actually connecting to your API. So this depends on your use case. Then we include a hash of the full query document. We don't want to include the actual query string itself. Here we've kind of normalized and stripped white space before hashing it. Next is another hash, and this is all the JSON encoded GraphQL variables. And the operation name as well. A GraphQL document can contain multiple operations, but we only care about the one that's currently being executed. So if your document contains multiple operations, you know you have to pass in the operation name that you want to be executed. So these last three parts that I've highlighted, these are all standard inputs. We saw this earlier for any GraphQL request, so they have to be part of our cache key. And finally, I'm going to include this kind of mystery version. This is very Shopify specific, so I'm not going to get into too many details, but basically we have an existing caching strategy that we use throughout our code base in our REST APIs and GraphQL, et cetera. So this is like a version that's bumped when certain resources are changed. So going back to our kind of product example, someone changes a product, this version ends up getting bumped. So this implementation may depend on your use case. If you already have something like this, you can use it. Oftentimes this might be like a combination of updated at timestamps across your resources. But going back to this, like we know that a product type is backed by our product model, which is already part of this cache strategy. So that's why that we know that we can set this to be true. So putting this all together, we now have a full query cache. If the query is in our cache, the entire result is served from our memcache, and this avoids GraphQL execution entirely. So this is every single resolver is avoided, and often GraphQL execution itself for a complex query can be quite expensive, especially if you have external calls or database calls happening. So we're avoiding all of that. So let's talk about the impact of this cache. So these are cacheable requests. It shows which queries are even cacheable or not actual cache hits or misses, just if they're cacheable. This top line is all requests, and the next one under that is cacheable requests, and the bottom flat one is requests that aren't cacheable. So in our API at least, about 85% of requests are cacheable. That's pretty good. The higher this number is, the better performance gains you could theoretically see. And most APIs are read heavy with less writes, and GraphQL APIs shouldn't really be any different. So, but the less cacheable requests you have, the smaller the performance impact is going to be. And I think this is the good one, response times. This is average response times for cacheable requests. So the average miss in this short time period was about 500 milliseconds. And the average hit was about 70 milliseconds. It's also noticeably smoother with less variance. So this is obviously a huge difference. An improvement which is not only better on, say, Shopify's infrastructure and servers, saves us money, causes us less potential issues, but this provides a way better experience for any client using the API. They're obviously getting really fast requests with less variance. So there are some downsides. No caching solution's perfect, and let's talk about some of them. First of all, our solution is opt-in. This is done as a defensive measure. So I've already talked about how we decide to opt in to this caching. But one downside is like this does mean that as our schema evolves and we're adding new types, we can forget to opt in. And that could drop our cacheable rate. So it's important that we always, I guess we come up with some tooling to try and automate this, but generally we need to just consciously think of, okay, we've added a new type. Does this work in our existing caching strategy, and can we opt into cache? These next two are mostly dependent on how much traffic your API gets and who the clients are. If your API is only used internally by your own client, these two probably won't be much of a problem. However, if you have a large public API like ours, the sheer number of potential documents can put stress on your cache store. So storage size could be an issue, and we're storing the entire serialized response. So if you're asking for a large document with 250 products and sub-connections, the response can get large. Many APIs have ways of limiting query complexity or depth, for example, so that could be one way of limiting it. This last one's a little more interesting, kind of described as cache key explosion, but it also has to do with cardinality. So that's just the number of different query documents that your API is receiving. So if you have a lot of different requests coming in, you're going to be generating cached items for each one of those. And you run the risk of evicting other cached items in your store. And if that like eviction rate is high enough, you're going to start kicking out other cached items that will have an effect on your performance. So in our case, we haven't actually seen this to be a problem in production yet. We also have some large cache stores, which helps. But that is one thing that you could end up hurting your performance, probably more than helping it, if you just keep kicking out cached items from your cache. So these are some things that, if you're thinking of this, you'll have to look out for. But again, if you're thinking of this for an API that's only servicing a couple of your internal controlled clients, the like cardinality or the variety of your query documents are probably fairly limited. So I don't think this should be a problem in practice for most people. And that's it. So I hope you've learned a little bit more about GraphQL caching, and hopefully that losing HTTP caching isn't the end of the world. There are some strategies to use, such as this one. This is kind of the best case. Again, like a full query cache is all or nothing. And when you get the all, that's really good. Thank you.